Hello, I'm Osama Reis. I'm a research scientist at Rensselaer Polytechnic Institute, and today I would like to give some details of the procedures used on current quantum computers for estimating expectation values of observables. This is a very elementary procedure used for a lot of quantum algorithms, especially the variational quantum algorithms, and there does not seem to be enough information online on how this procedure is done step by step. So I hope this is of value to researchers and practitioners in quantum computing. Let's start with a very simple example. You want to execute some quantum circuit. You have some arbitrary quantum circuit, and you have some measurement operations at the end. When you put these together, you are sampling quantum states at the end of the quantum circuit. This is typically done using the sampler primitive in Qiskit. If you add some Hermitian or unitary operator to the mix, you are estimating expectation values of some quantum states. And this is usually done using the estimator primitive in Qiskit. Now, many important and early applications for quantum computers require expectation values. This is usually to get some observables like the ground state energy in the case of quantum chemistry or quantum materials, and electronic structure problems are just one of the applications that require measuring or expectation values. But how do you actually do this on a quantum computer? Libraries like Qiskit are doing this automatically under the hood. So I think it is of value to kind of take a peek under the hood and try to do this ourselves and get a better understanding of expectation value computations. Let's consider that we have some operator O, and we are trying to compute the expectation value. And we are assuming that we are given access to some operator O on the quantum computer, and we have some procedure to prepare the state psi that we want to compute the expectation value of. So there are a couple of methods to do this. One very simple way is to do a Hadamard test. Let's say O is some unitary operator, and you can execute these two quantum circuits to get the real and imaginary parts of the expectation value. This method scales as order of 1 over epsilon squared in the number of samples you need to converge to a precision of epsilon. Another method is quite elementary. It's widely shown in textbooks and in research papers. This is quantum phase estimation. Once again, you have some unitary operator O, and you want to compute the expectation value. You can execute this sort of quantum circuit. There are two circuits that I have shown over here. You can do this bit by bit using this circuit, or you could try to get the entire thing using the quantum Fourier transform. There are many different ways to do this. These are just two examples of the way you can do this. There are iterative quantum phase estimation methods. There are also some phase estimation methods that can use runtime primitives. However, the good thing about this procedure is that it converges as 1 over epsilon. So you don't require as many samples as the previous method that we discussed. However, you can see that these methods require a couple of ancilla qubits to run on quantum computers. And they also require controlled operations, which are not cheap on current devices. One other thing that you can do is you can just diagonalize your operator and sample it. So in this case, let's say O is a Hermitian operator or a unitary operator, and it has the diagonalization V, VV over here. So you can just apply the eigenvectors V to your quantum state, and then you can measure in that basis and do some post-processing to get the expectation values. This method converges as 1 over epsilon squared. So it's not the best way to do this, but this is very amenable for current quantum devices. Now, the method that we are going to focus on is this method. And this is what is being done under the hood when you call the estimator primitive in a library like Qiskit. Now let's go over the ingredients for this procedure real quick. You have some arbitrary quantum circuit. I'm going to call this quantum circuit Q. And this is going to prepare my state psi, of which I want to compute the expectation values. U is a unitary operator, of course, as expected. The second part of the puzzle is the operator itself, of which we want to compute the expectation value. This is typically given as a sum of sparse Pauli strings. So Pauli strings are these things over here. You have Pauli operators, and these are Kronecker products. And these are some coefficients for the Pauli strings. I'm going to use this notation over here to represent this sparse Pauli sum. This is a tuple of the Pauli operators that are in each piece of the string. These are the coefficients. And these are the Pauli operators, where I can take the place of either the identity, you can have the X, Y, and Z gates. And this is a Hermitian operator. So it's going to have an eigendecomposition with real eigenvalues. Now, by the definition of the expectation value, we can just take this operator over here and we can substitute our Pauli strings in there and we get this term over here. And by linearity of expectation values, we can just take this sum outside. Now note that some people use this kind of notation to represent expectation values. In my case, I'm going to keep using this since it makes things much clearer in this context. Now, if we look at measurements on quantum computers, usually we are sampling some bit strings at the end, and we are going to sample them with the corresponding probability of each basis state, the computational basis. However, when you are talking about expectation values, you're getting some scalar out of the quantum computer. So these are clearly not equivalent to each other. So what are the missing links between these two operations? Now, if we look at the form of the Hamiltonian or the operator H that we have, we could simply try to diagonalize the operator, and that could kind of do the trick. We can take the diagonal matrix outside, and now we have something that looks more like sampling of bit strings. Of course, this is not feasible on quantum computers because the matrix is going to be very large. The H is very large. And of course, if you already have a diagonalization of H, usually you don't want to do further computation because that is solving the problem in the first place. For example, if you want to get the ground state energy of H, then diagonalization already gives you that solution. What is more feasible and sensible is to look at diagonalizations of the summands of the Hamiltonian. Now, in our case, these summands are Pauli strings, and we can diagonalize each of these Pauli terms individually, since these are small 2x2 matrices. And we can apply these eigenvectors to the quantum state and prepare these quantum states instead. Psi tilde, psi prime, sorry. Now we have this giant diagonal matrix in the middle. We can take this diagonal matrix outside, and now we have something that looks more like sampling of bit strings with probabilities. The diagonalizations of Pauli matrices are shown over here. Using these diagonalizations, we can actually form this diagonal matrix that we took outside. We can compute these terms individually. Now, for an example, let's say this is our Pauli string. The diagonal matrix corresponding to these Pauli strings is as follows. And for these particular terms in the diagonal matrix, you can compute these using parity. As an example, let's say we have that same Pauli string, and we sample this bit string given over here. We can turn this Pauli string into this Pauli string of the diagonal matrix into a bit string, and we can take these two bit strings together and compute the bitwise AND of each term. And finally, we're going to compute the parity of this final bit string. And if the parity is odd, then this term is going to be -1. Otherwise, it's going to be +1. Now, as a summary, we have this quantum circuit U to prepare the state psi. Now, to get the expectation values, we're going to sample in the psi prime basis instead, as shown over here. And we are going to do this for each Pauli string. And we are going to sample over the states and compute these DII, DKK values over here. And we are able to estimate the expectation value. We can further optimize this by grouping together commuting Pauli strings. And we will go over that detail too. But for now, we can go over the demo. What I have here is a Jupyter notebook implementing these procedures. And we'll do this with a couple of different approaches and try to compare the values with what we get using Qiskit's built-in procedure. Now let's define some random quantum circuit and define some corresponding Pauli observables. Now, as to set a baseline, let's measure each Pauli string using the Qiskit estimator primitive with nearly 1 billion shots. So these are the expected outcomes for each Pauli string. We can repeat this process by using linear algebra. For each Pauli string, we can compute these values. And these values do indeed match up to the precision of the sampling we have used. Now we are going to go into the more involved process. We are going to replicate the procedure that is used on real quantum devices. We're going to diagonalize each of the Pauli strings. We're going to sample these bit strings in that diagonal basis, and we're going to post-process the results to estimate each observable. So these are the diagonalizations for these Pauli strings, and therefore these are the quantum states that we are aiming to prepare and sample in the computational basis. So I have this code over here to do all of this automatically. So I'm going to create separate quantum circuits for each of these Pauli strings. We have the eigenvectors being applied at the end of the quantum circuit. Now I'm going to sample these quantum circuits. I have the quasi-probabilities over here in this array. I have the bit string. I have the coefficient over here. And I have this for each of the 4 Pauli strings that we had. Now we can post-process these bit strings. What we're going to do is for each Pauli string, we're going to get the quasi-probabilities. We're going to get the coefficients and try to post-process them to get the expectation value. First, we are going to build the Pauli bit string to figure out what our diagonal matrix is. And then for each of the samples that we have collected, we are going to get the corresponding element of that diagonal matrix. And as I mentioned earlier, we are going to perform a bitwise AND operation and then compute the parity to get that value in the diagonal matrix. Then finally, we can combine everything together to get the expectation value. So this is all of the post-processing that is being done for these bit strings. And what we get in the end is something that is very close to what we were expecting. These are the results from the Qiskit primitive with 1 billion shots. These are the results from the procedure we have implemented with 1 billion shots. As you can see, they are close within the sampling arrays. And this is the exact result that we expect from linear algebra. Now let's talk about the further optimization that we can do for these observables. As I said, these Pauli strings can commute. And there's a theorem that says that if Hermitian matrices share the same eigenvectors, they have to commute and vice versa. So therefore, if you have 2 Pauli strings that are commuting, they have the same eigenvectors. And what we can do is we can prepare the same psi prime state for those 2 different Pauli strings. And we can share those eigenvectors between them and figure out things in the post-processing part instead of doing this separately for each Pauli string. This can significantly reduce the amount of samples that you need to get from your quantum computer, since the number of Pauli strings can be pretty large. Now, let's look at a couple of examples of how these Pauli strings can commute. Let's say we have these 3 Pauli strings. You can see that Pauli strings H1 and H2 are commuting termwise. That is, each of these commute termwise. So it's pretty straightforward to figure out the shared eigenvectors. In place of the identity, you can just put the Hadamard gates over here. And then you can combine everything together. And this is the diagonal matrix that is being formed at the end. And we can figure this out in the post-processing part. And we have reduced the number of samples that we need to get by a factor of 2 for these particular Pauli strings. Now we can consider computation in general, which is not qubit-wise. As you can see, bit strings H2 and H3, they do not commute qubit-wise. Like all the particular Paulis are not commuting with each other. However, as you can see over here, the last Pauli matrices do commute with each other. And you can use that to show that this indeed is a commuting set of operators. Now this figuring this out in a fast manner and figuring out the shared eigenvectors for these uh, kinds of polystreams that are commuting in general, not qubit-wise, but in general, is an active area of research. And I will leave you with this reference of a paper that was published just a few days ago as of recording this video. Thank you, and I hope you found this insightful and productive.